Now we'll look at some basic identities and algebraic manipulation. All right. These are all identities you have possibly been taught in Math 42. We'll just recap this. So any variable or 0 is that variable. So x or 0 is x or 1 is 1, x or x is x or x bar is 1. You can can imagine like x can take 1 or 0. So one of this term will be 0, another term will be 1. So it will become a 0 or 1 kind of operation. So ultimately, end of the day, it becomes 1. And x bar of whole bar. So if you complement a variable and then again complement it, it basically revert to the original variable. So x complement of x complement is x. Similarly, we have x dot 1 is x. It means x and 1 is x and 0 is 0, x and x is always x, and x and x bar is always 0. Now look at or notice this specific like observation between these two columns, like 1 3 5 7 9 and 2 4 6 8. Okay, 1 and 2 has a dual relation, isn't it? Like if I make a dual of 1, I get a 2, like 2. If I make a dual of 3, I get 4. If I make a dual of 5, I get 6. And if I make a dual of 7, I get 8. This observation actually leads us, or this observation confirms this statement from Boolean algebra that if a relation is true, like if a relation holds true, means here the relation is x or 0 is equals x, that is a relation. If that holds true, then its dual relation also holds true. That means if you individually makes dual of the right hand side and left hand side, they also their relation also holds. So in this case, our original relation was x or 0 equals x. Now you make 12 of each of this left hand side, right hand side expression, and you get x dot 0, sorry, x dot 1. Remember, in the dual, you need to change 0 to 1 and 1 to 0. So x dot 1 equals x. That relation also holds. So with that observation, you can also say that this 10, 12, 14, 16 is, if they are kind of true in their relation, then 11, then it also imply with a dual nature, dual equivalency nature, 11, 13, 15, 17 also holds true. Well, so that's a different things to understand, but let's understand these 4 very important properties of, or a basic identities we say it, of the Boolean algebra. Like commutative property, it holds just like algebra. Like if x or y is equivalent to y or x, you can change the position of the variable. Similarly, it's dual, x and y is equivalent to y and x. And associativity, that is also kind of very similar to Boolean algebraic properties. X or normal algebraic properties is the same. Associative properties holds also in the Boolean algebra. X or y or z is same as x or y or z. Similarly, x and yz is equivalent to x, y and z. Then distributive, like if you kind of now, like I believe most of you are thinking plus as like in terms of or, not really or, but in terms of plus addition operation, and dot in terms of and, not really dot in terms of multiplication, not really and. But I'll suggest that please start thinking, at least when you are doing Boolean algebraic problems, change your thought process. It's not easy, like to think plus as or and dot as and. Instead, we always think of dot as a addition, sorry, dot as a multiplication and plus as a addition. Why I'm saying that, it will be very clear in the distributive identity. Okay, So see, like x and y or z is x, y or x, z. So we are distributing x over y, z. Not distributing x really, we are distributing this and over the or, okay, through this variable x. So it becomes xy or xz. And which kind of corresponds to our distribution of the multiplication over addition as well. Like think of this is a normal algebraic expression, x multiplied by y plus z. We can very well write it down as an x multiplied by y plus x multiplied by z, which is distribution property of the normal algebra, which holds also in the Boolean algebra. However, in Boolean algebra, we can distribute the or over and, as in 15, distribute the or over and then if there is any x or yz, it will be equal to x or y and x or z, which does not true in normal algebra. We cannot distribute addition over multiplication, right? Now here in the Boolean algebra we can do it, and I found usually students, in terms of like reducing a Boolean expression, we pretty much tend to overlook this relation of distributing or over and, because our brain is tuned to kind of make these rules associating with the normal algebra, like in terms of addition and multiplication. But since Boolean algebra, they are not really addition and multiplication, they are really and or. They goes through different properties and operations, right? So please make sure you remember this fact always. In the Boolean algebraic world, you can distribute this plus, which is or, over dot, which is and. And last row, but not really the least, not in any sense, and probably it is the most important law in the digital logic design area, is called De Morgan's law. It is not like any other, like you cannot associate that with any normal algebraic relations, and De Morgan is used quite often to transform one type of circuit into another type of circuit, and you will see throughout our next couple of lectures we'll be coming back to De Morgan's one after another. Okay, now what this law says is this simple relation: if you are inverting a or relation, that is x or y, you are inverting them whole, this is as equivalent as x bar and y bar. This, and if that is true, then we have xy whole bar, like dual relation is also holds, right? So that means dual of x plus y is x and y equals x bar, and you are changing and to or, so x bar or y bar. So De Morgan's law, x or y whole bar is x bar and y bar. Also xy whole bar equals x bar or y bar. So this is De Morgan's law, and please remember this law very carefully because it is widely used. Now let's take a small example for the Boolean algebraic manipulation, and please find out in internet. You can search in internet and you will see tons of such problems, which gives you a function in the terms of Boolean expression, and it calls, okay, go and reduce it as much as possible. Please practice it a lot. Okay, so we won't be giving much practice in the class probably, but with the fact, assuming that you will search in the internet, you will see tons of such examples, such exercises. Please make sure you do that. And this is nothing but recap of your Math 42, and I'm assuming in Math 42 you did a lot of practice such practice of the Boolean, not Boolean, in the logic manipulations and logic reductions. Okay, so this example says, okay, if my function, I should have written xyz, but let's assume this is a function of involving variable xyz, is x bar y bar or x bar yz or x bar yz bar or xz. And then what we can do, we can, by identity 14, we can rewrite this expression at x bar y and z or z bar or xz. Z or z bar is 1 by identity 7, then it becomes x bar y or, and 1 or xz, and then by identity 2, x bar y and 1 is basically your x bar y, and xz remain unchanged, so your reduction becomes x bar y or xz. Now the question is why we are interested in reducing Boolean expression. The root cause or root reason that we are interested in digital logic area about reducing Boolean expression is business. Okay, is sole reason is the business. Let me explain this. Let's say for some problem that you are trying to map it in and make an, for some problem you are trying to make a digital circuit to make a solution for that problem, and you come up with the final function like this, like f x y z. We have 3 independent variable, and that express that x bar yz or x bar yz bar or xz. How do you implement it? You will take 2 OR electronic component which can perform OR. You need to take 1, 2, 3, 4, 5 AND component. So 2 OR component, 5 AND component, and you need to take 2 inversion negation component, electronic component. So you are getting like 2 OR, 2 NOT, and 5 AND. So total like 9 components we're talking of, 2 plus 2 plus 5. And now if you see that you can reduce this expression into x bar y or xz, which is equivalent with each other, then to implement a logical circuit, electronic circuit, we need to pick up only 1 OR, 2 AND, and 1 inverter. So 1 OR, 2 AND, 1 inverter, which is 2 plus 1, 3 plus 1, 4 electronic component. So in my larger expression, I needed 9 electronic component to implement. In reduced expression, I need 4 electronic component. Then, of course, for larger expression, cost is more. Reduced expression, cost is less. More cost means less profit. Less cost means more profit. So there you go. Here's the business need. So that's our target in our digital logic. That why we are more interested in reducing a bigger expression into the smaller expression. Okay, because it reduces the cost of the corresponding digital circuit. Now we can have some more commonly used theorems for Boolean expression for simplification. And these 2 column 1, 2, 3, 4, 5, 6 shows that, and of course like 2 columns are kind of dual of each other, and they are commonly used, and they are actually can be derived. They are not a basic identities, they can be derived from the basic identities, but it's kind of used so widely in our Boolean expression reduction problems, they kind of treated as identities. You can just apply them directly in your reduction step, which says x or xy is x. Okay, so how do you do it? You distribute OR over and you get it. Not really. No. So basically what you need to do is basically this becomes x and 1 or y, which is x. So let's do that. This is very interesting things. I'll just write it down and I'll try to make sure you understand how this is achieved. Okay.